Hello, advanced algebra students, and welcome back to another video lesson as we continue exploring exponential growth and exponential decay. Today, we're really focusing on solving problems that involve exponential growth and decay, more real-life scenarios, if you will. First, I want to go through a series of quick practice and questions. So number one, consider this equation. Is this growth or decay? And what is the y-intercept? This is growth because the b value is 5, so that's a growth. We're above 1, so b is greater than 1. What is the y-intercept? 7, right? That a value out front represents our y-intercept. We're starting with something, and it's going 5 times that amount every some unit of measurement. Number 2, consider this equation. Is this growth or decay? And what is the y-intercept? Again, this is growth. This b value is greater than 1, so it has to be growth. The y-intercept, 2.5. That's our a value, and that's where we're starting with. Maybe we've got $2.50, and it's growing by 1.7 every day. Who knows? Next one, growth or decay, and what is the y-intercept? This is decay because my b value is between 0 and 1. Right? We got to be between 0 and 1 for decay. And the y-intercept is 4. So we're starting with 4 of something, 4 units, but it's decreasing by maybe 18% or something along those lines. Third one, or the fourth one, is a little bit of a challenge. We've got 2 points, one here at 2 and one up here at 6. Each one of these is going to represent a half of unit. So this would be 1, this over here would be 2, and then 3, and then 4. Can you write the exponential equation to represent an exponential function that goes through those 2 points? Again, in general, we have y equals a times b to the power of x. A is our y-intercept, so that's 2, times our growth factor. We went from 2 up to 6. What do we multiply by to get from 2 to 6? We multiplied by 3. So y equals 2 times 3 to the power of x. And again, we're looking for that growth factor. So those are all what we call the basic exponential properties and what we're looking at for exponential functions. But now we want to really apply these to story problems. So here's the first example. Within the past year, price of Tesla stock has more than tripled. If you see, or if you have $5,000 in a stock and the stock triples each year, write an equation to represent how much money your stock would be worth in X years. Y equals a times b to the power of x. What is our starting amount in our stock? $5,000 times, what's this growth factor? Well, the key word is that it triples, which means we're multiplying it by 3 to the power of x. 5,000 times 3. So tripling means 3 times that previous amount. So at 1 year, we would have $15,000. At 2 years, it triples again, 45,000, and so on. If we wanted to figure out 10 years, we would plug in a 10, and then we would need to use a calculator. Let's go to Desmos. 5,000 times 3 to the power of 10 gives us a lot of money. $295,245,000 if it kept tripling. Okay, but tripling 3. The next one, a zombie virus is spreading. There are 3 zombies at the start, and then the zombie population doubles every 2.5 hours. How many zombies are there going to be after 25 hours? Boy, a lot of things happening. So again, y equals a times b to the power of x. Our starting amount, or our starting zombie population, is 3, and it doubles. So times 2 to the power of x. So there's our general formula for this scenario. We're starting with 3 zombies, and it doubles. We're multiplying by 2 every 2.5 hours. So we've got to use this piece of information along with this one to figure out how many zombies there would be after 25 hours. Okay. Normally, we might just be able to stick in 25 because it might double every single hour. But the problem we have here is it takes 2.5 hours to double. So what we've got to figure out is how many 2.5 hour segments are there in 25. And so what we actually end up doing is taking 3 times 2 to represent the doubling to the power of 25 hours divided by the frame that it takes. The total amount of time we're looking at divided by the amount of time for it to double or triple. So 25 over 2.5, which is also 12. So times 2 to the power of 12. We have 12 periods where it's going to double. So we can go back over to Desmos. 3 times 2 to the power of 12. 12,288. 12,288. So after 25 hours, we would have 12,288 zombies. Okay, so a few more different things. Again, tripling was 3. Doubling is multiplying by 2, that it's doubling every time. And we worked a little bit yesterday with percentages, like we're going to have in this one, in a sense. Radiation levels at Chernobyl were over 600 MSV at the time of the meltdown in 1986. The half-life of that radioactive material is 31 years. So after 31 years, it cuts down to half. And then after 31 years, it cuts down to half. A human has a higher risk of cancer at 100 MSV. So if the levels are at 100 or higher, it's still a little bit risky. So is it safe to go there now? Here's the key in this one, half-life, right? Half of it. And so if we look at half-life, that means we have 50% left or 50% gone. So y equals the starting amount, which is 6,000, times 1 minus the 50% to the power of x. Right? We're losing 50% half-life, which is 0.5 to the power of x. Now, what we have to be careful of with this one is that in 31 years, half will be left. So in 31 years. So what we need to figure out is how many years are from 1986 to now. Or 2021, take away 1986. 35 years between now and then. So it's been a total of 35 years. So y equals 6,000 times 0.50. We've gone 35 years, but we have to divide it by the amount it takes for a half-life, which is 31. 35 over 31. And we can plug that into Desmos. Okay, so 6,000 times 0.5 to the power, and I'm going to put it inside of a parenthesis, 35 years divided by 31 for the cycle that it takes, gives us 2,743. 2,743 MSV. Is it safe to go there now? If you have a risk, if it's 100 or higher, it's not safe yet. We probably shouldn't go to that area because it still has some radiation levels that are over that 100. Okay, half-life is 50% though, 50%. And again, anytime that we don't have an exact time frame, 31 years for the half-life, or if something is doubling every 10 years, we have to make sure we divide by that number. So you get lots of examples of story problems today. Don't forget 2 key pieces. Growth means we have 1 plus the percent, and decay means we have 1 minus that percent. But we need those decimal forms, percents as decimals, if we're going to use them. If you have any questions, please make sure that you reach out. Otherwise, until next time, everyone, stay safe.